So, now, let's find out what would it be like if you were going to Jupiter and then you landed your spacecraft and now you want to get out of Jupiter because it's boring and windy and stormy and all that good stuff. Well, so let's find out. That's what the first example this script gives us here. We want to know the escape velocity for Jupiter. So that means then we need to find the mass of Jupiter, and we need to find the radius of Jupiter. And it turns out, I looked this up, because that's how clever I am. The mass of Jupiter is 1.90 times 10 to the 27th kilograms, which is way heavier than Earth, at least 1,000 times heavier. And the radius of Jupiter is 7.15 times 10 to the 7th meters. And that's like 20 times bigger than Earth, just from a radius aspect. That makes it like 400 times the, more like 8,000 times the volume of Earth. Anyway, regardless, now I'm just showing off. The escape velocity then is going to be 2 times 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. That's our capital G value that we have right there. Then the mass of Jupiter instead of the mass of the Earth, which we said is 1.90 times 10 to the 27 kilograms, divided by the radius of Jupiter, which is 7.15 times 10 to the 7th meters. And that whole thing is taken to the 1/2 power, square root. And when you punch those numbers, you get 5.95 times 10 to the 4th meters per second, which is right around 8 times the escape velocity of Earth. So, it's not as difficult leaving Earth. It's going to be even more difficult leaving Jupiter. All right, the next thing I want to talk about is geosynchronous satellites. If something is geosynchronous, the word geo comes from the Greek word for world, and synchronous in both Latin and Greek means time, so it's dealing with world time. And so geosynchronous is basically saying you're going to move with the world at the same time. Okay? Now, so if we want to calculate the velocity of a geosynchronous satellite, well, we know that it's going to be 2 pi radians per 24 hours. But we want it in meters per second to figure out, or even miles per hour if we want to, but we're going to go with the SI value, or meters per second. And so what we're going to do is, since radian means the radius, we're going to have to find the radius of the Earth plus how much higher above the radius of the Earth it's going to be. So this is going to be radius of the Earth plus extra. How much higher you're going to be, and it must be expressed in meters. And on the bottom here, we're going to convert 24 hours to seconds. We know there's 3,600 seconds in 1 hour. Rather than keep converting that all the time, and that turns out to be 86,400 seconds. Per 1 hour. Probably should have cut off my conversion there, so that was not good of me. So I put one radian here is equivalent to that. That's the radius, and then 1 hour, or rather, one. Well, let's just say 24 hours over 86,400 seconds. That way, 24 hours is gone. And the radians are gone here. So I'm going to take 2 pi times that length divided by 86,400 seconds. That's the circumference of the gigantic circle of the geosynchronous satellite traveling around the Earth. Divided by 86,400 seconds will give us an answer in meters per second. Okay, so the problem they asked there was, let's suppose that we have a satellite 200 miles above the Earth. And the question there is, what is going to be the velocity of the geosynchronous satellite? So VGO, I used to call it GeoMetro. It couldn't even get around my driveway much less the Earth. It was pretty bad. Anyway, so this is basically the formula we're going to use. We're going to use 2 pi times total radius over 86,400 seconds. Okay, so we need to figure out how many meters is 200 miles. So 200 miles, the conversion I always used in Chem 1 was that 1 kilometer was equal to 0.621 miles. And then we're going to change that to meters by converting it like so. So kilometers gone, miles are gone. This leaves us meters. Okay? Now, we also know that the radius of the Earth is 6.38, 2 pi times 6.38 times 10 to the 6th meters, plus whatever this turns out to be. And it turns out that is 3.22 times 10 to the 5th meters. So we're going to add 3.22 times 10 to the 5th meters to that, and then divide that whole thing by 86,400 seconds. And it turns out that value is 480 meters per second. Now, in miles per hour, that's approximately 1,080 miles per hour. Of course, if you're that far above the Earth, and you're looking down the Earth, you don't think you're moving at all. The fact is, we're probably moving not too far from that as well, about 1,000 miles per hour. This is why when we slam into a planet, if that should ever happen, the last words out of our mouth is, oh, and then we're going to be smashed because we flew against one of these 2 walls, depending on which direction we're going. All right, so that's how you do escape velocity and geosynchronous problems. You have some practice problems to do with that. These 4 problems right here. It's in your script. Hey, have fun!